All right, so welcome everyone. So I'll be doing today's lecture and Wednesday's lecture. And so, am I on? I'm on, good. Okay, so the topic is randomized algorithms, which is a huge topic, but I'll just say gentle intro to randomized algorithms, part 1, and the next lecture will be part 2. So what is a randomized algorithm? A randomized algorithm flips coins to decide its output. So normally if you think about algorithms that you've done, like BFS or any graph algorithm, it's deterministic. Like it doesn't have any random behavior. So to give you an example of a randomized algorithm that you probably know is, for example, randomized quicksort. Right? So hopefully you all remember quicksort. And you may or may not remember what randomized quicksort is. So let's just recall how quicksort works. So what does quicksort do? Quicksort starts with a pivot, right? So it looks at, let's say this is your array A, and I don't know, let's just say index 0 to n minus 1. It picks this as the pivot. And then it takes everything that's less than the pivot, puts it on the left. Everything that's more than the pivot, puts it on the right. And then recursively calls in those. Alright, so what does it do? Basically, it has this sort of, this neat partition algorithm, but you change this into everything less than A0. You put A0 here, and this is all more than A0, and then you do a recursive call in each. Right? You guys remember this? And let's not worry for now if what happens when certain elements are the same. Let's just assume they're all distinct, just so that we can get rid of the the coding complexities and get into actually how the algorithm works. So do you remember what the bad case for quicksort is?
Sorted.
Yeah?
Sorted.
So if the array was actually that, then the pivoting doesn't do anything. And you end up with essentially the same thing. And then basically your running time becomes quadratic. So to fix this algorithm, you might think, let's come up with a more, so what is the right pivot? What is the right pivot to choose? Yeah?
Number that's close to the middle.
Something close to the middle, right? So you could split into even halves and then it starts to look like merge sort. So the ideal pivot is the middle element. But then figuring that out would be too complicated. So you might think, okay, I'm going to come up with some complex strategy to try to figure out something close to the middle. And so people do this. What they'll say is, well, maybe you could look at the first element, the middle element, the last element, pick the middle of those three and use that. Or you could say, break it up into groups of 5, and in each of those pick the middle element, and maybe pick the middle of those, or something like that. But instead, what randomized algorithms do is often give you a very simple randomized solution, which is very easy to code, but hard to analyze, right? And so I'll show you the easy randomized quicksort, and we'll actually do the analysis, and that'll give you some sort of flavor of how randomized algorithms work. So let me write out randomized quicksort. So I'll just call it randomized quicksort of some array A. I'm not going to write what the base case is and what happens for constant length and all that. I just want to give you the overall view. So first, what you do is you pick a random and technically uniform random pivot. What that means is you just pick something uniformly at random from here. right? So this is the flipping coins. So you pick a uniform random pivot, say, I'm just going to call it AI. Yeah?
Can I just throw in quick? Uniform at random means that we pick each element with equal probability. Like they're all equally likely.
Yes.
In case. Sorry.
No, thanks. Yeah, so what that means is each of these is picked with probability 1 over n, where n is the length. So you can imagine you're just going to pick a random number from 0 to n minus 1, and you set that to I. Maybe I will call it a R to denote the random index that's picked. And then now there are ways in which you can partition, but what you do is you can just say construct L elements less than AR, construct, I'll just say the array of elements that are less than that, and then you construct R, the array of elements that's more than AR, maybe I'll make it greater than equal to AR, right? And then you just do randomized quicksort of L. Also get rid of this. You do randomized quicksort of R, of the left and right halves, and then you stitch it together, right? You just output. So let's just assume that what this does is that this actually is going to sort everything and output what's sorted. So you output L, the rth element, and then R. Make sense? So it's the same thing as quicksort, you just pick the pivot uniformly at random. So it's a really simple fix in terms of the coding. And technically, if you really wanted to write code, you wouldn't do it this way. What you would do is you have vanilla quicksort, you simply switch this with the first element and then run vanilla quicksort. Right? Because vanilla quicksort would just pick the first thing as the pivot. So you simply pick a random element and move it to the front. But I think it's useful just to see what's happening in terms of recursion. Yeah, any questions? Good? Okay, so what we want to say about randomized quicksort is, well, actually, before we do this, let's just try to understand what happens. Because, if you think about this a little bit, you'll see that there is some probability that the worst behavior will happen. Right? So if pivot is always the minimum, or the maximum of A, then the running time, so I'll denote the running time as just T of n, and I'll say worst case is essentially going to be something like theta of n squared. Even if the array was not sorted, if you always pick the first if the pivot was always the first or the last element, then you have the problem. So there is some probability that this bad behavior still happens. On the other hand, if pivot is always the middle element, I should say instead of the middle element is always the median, then what you get is you kind of get the right recurrence. You'll get T of n is 2 T of n over 2 plus O of n, and this is O of n log n. Right? So if it was lucky enough to always pick the middle element, then you get the right behavior. And what happens is something in between. And every time you run it, you get something different. Right? And so this is a randomized algorithm. And the aim of the analysis is to actually show that we're almost going to do this, even though we don't know what the median is. Even though the random choice is just picking randomly without, it's not looking at the values of the elements at all. like this step. So it's almost sort of magical that it should work. So any questions about what this is? Make sense so far? Okay. So I'm going to get rid of randomized. I'm going to remove this algorithm. No, actually, let me keep this. Let me get rid of this instead. Okay. What we want to prove, or we hope to prove, so this is really important. So for all inputs of length n, for all inputs of length n, the running time is O of n log n. But now the problem is, what do I even mean by the running time? Right? Because the running time differs depending on what the pivot is. So what we do is we instead say the average running time. Does that make sense? And what is the average over? So what is the average over? The question makes sense? What do I mean by average? Yeah?
You take the running time of all, like a bunch of runs and just average all of the times together.
Intuitively, that's what you want to do, right? You want to say, if you ran this over and over again for the same input, you fix an input and run it over and over again and see what the average is going to be. So this is the average over the randomness of the algorithm, which in this case is step 1. So this is really important, and this is often a point of confusion. There is no averaging over the input. I'm not saying that for a random input, randomized quicksort works fast. I'm saying for all inputs, the average runtime is n log n, and the average is over the randomness of step 1, of choosing the pivot. Right? It's important. This is often a common point of confusion. Actually, even amongst people who are even amongst researchers who are not in this area, will often think that a randomized algorithm is one whose behavior is like some average over inputs. This is saying that there is no such thing as a bad input. There are only bad choices of the algorithm, but you can average over those. So even if you gave it something that was sorted, it would still work fast. Okay, so does this make sense? So we have to define this, which I will do formally, but yeah?
So does this mean that it doesn't necessarily mean that a randomized algorithm is going to be better than doing any other way, because of the fact that you'd have to do it over and over and over again in order for it to average out?
That's a good question. So this just says that the average is low. What typically you can also prove is that with high probability the runtime is low,
Okay.
which actually means that this is harder to analyze, but you can say that the probability that randomized quicksort takes much more than that is actually extremely small.
Okay.
So not only is it just on average, they'll say it's also true with high probability. But first you start by analyzing the average, and then you do the high probability. So it's not just that, and yeah, so does that answer your question? Does that make sense? Okay. Okay, any questions about this? So to be able to sort of define this clearly, we have to do some discrete probability theory. So we'll do a very quick, short introduction to discrete probability theory, just enough to be able to come back and analyze this. Right? So again, I guess you have an intuitive sense of what this means. So now let's do it formally. Okay, so now there is a gentle introduction to randomized algorithms, now an even gentler introduction to discrete probability theory. Probability I mean, it's basically just probability theory. But the reason I want to emphasize the discrete is it makes lots of things easier. And I want you to sort of, to really think about it in terms of a discrete set of events. So how does this work? So usually you have omega, which is a set of outcomes. I'm just going to draw this way. So this is, if you think about this random process, each step is choosing a pivot, right? So suppose I just wrote down all the pivots that this algorithm chose. Those are the outcomes. This is like list of all pivots. That's the set of outcomes. Or if you want a simpler example, let's say tossing n coins. This would be basically whether it's heads or tails, right? All possible heads, tails, like sort of lists. Does that make sense? Like each coin is either a heads or a tails. So you could think of omega represents the set of all outcomes, and in this case it's actually a discrete set, right? In this you could represent it as permutations. Here it's like bit vectors, right? So in n coins there are 2 to the n possible outcomes, and here there's like n factorial possible outcomes depending on well, it's more complicated than just n factorial, but anyway, so the thing is there's some set of outcomes that you can think of. It's a discrete set. That make sense? So what is probability? Let's go philosophical, right? What does probability even mean? Probability simply says that you assign a number to each outcome. You assign a non-negative number to each outcome, so that the sum of those numbers is 1. That's what a probability is. We interpret probability in various ways, but at the end of the day, it's just saying that every outcome has a probability, but that's just a number, so that all these numbers sum up to 1. So probability is actually just a function from the set of outcomes to the non-negative reals, or non-negative 0, to the interval 0, 1. So let me write this here. When I say probability, you can actually think of probability as just a function to here, such that the sum of all, if I summed over all outcomes, that's 1. Now, you never think of probability as a function, but actually that's what it is. It's a function from outcomes to this range. Does this make sense? So every possible outcome has a probability, which is really this, and the sum of probabilities of all the outcomes is 1. That's what probability is. And if you get fancier, they'll call this a probability measure. When this thing is continuous, then things become more complicated. But in the discrete world, it's really easy for us to understand. And so in the case of all possible coins, if these are all unbiased coins, every outcome has the same probability. That's actually the uniform measure. So when you say uniform probability distribution, you just mean that all of these are the same. Okay? Right? Let me sort of go back here. Get rid of this. So, what is an event? So you've heard of events and probability, right? You've taken, yeah? What is an event? Can you define an event with respect to all of this? Define an event to me. Just tell me what an event is.
Think back to 12 balls.
What?
Something that cuts your probability space?
Any subset of outcomes is an event. That's it. Right? Yes. A event, which you can denote as E, is a subset of outcomes. And the probability of the event is simply the sum of probabilities of everything in the event. That's an event. So the nice thing about writing this way is that it sort of demystifies lots of things about probability. You just have a set of outcomes. Each outcome has an associated number. You call that number the probability. But in terms of the math often doesn't care. It's just some number. And then the probability of any event is just, the sum of the probabilities of each thing in that event. Okay? So there's nothing sort of mystical about this. Okay, so you understand this, you understand events. Now let's go one step further, the notion of a random variable. This is a little more complicated. So what is a random variable? A random variable is actually a function from this. So let's just suppose we said real value. But you can have all other kinds of values. It's just a function that maps every outcome to some number. So what is an example of a random variable? If you have n coin tosses, I could say the number of heads, the total number of heads. That's a random variable, because for every outcome there's some number of heads. But I could go fancy, I could say the number of 0, 0, 1 sequences in coin tosses. Right? If I did n ordered coin tosses, I could say how many times instead I should say tails, tails, heads, something like that. How many times did I see tails, tails, heads? That's a random variable. Right? A random variable is simply something that has some outcome that depends on this. Okay, so I'm going to remove, I'm going to keep this picture. Keep that. But now that we have this notion of a random variable, now we can talk about the running time. The running time of randomized quicksort on a fixed input is a random variable, where this is simply saying what are the pivots, and this is saying how many comparisons did it make, or what is the running time. Does that make sense? So I'll say the running time of randomized quicksort on a fixed instance, fixed input, is a random variable. What this says is simply, if you told me what all the pivot choices were, then the running time is just fixed. Yeah, questions about that? Is that clear? And now that we have this notion of now that you have this notion of a running time as a random variable, you can ask what is the average running time, right? Because it's the average over all of these. So that's how you sort of formally define your intuitive notion. Questions? Make sense? Okay. Now the technical term for average is called expectation, which is the expectation of a random variable, often denoted as E of x. So x is your random variable, and expectation is really our notion of average. So let's define this. How would you define this? Any guesses on how do I define this? Note that I have an expectation of a random variable. A random variable is simply a function from the outcome space to, let's say, reals. Probability is also a function from the outcome space to 0, 1, like the interval 0, 1. How do I define this? What should I write here? Any guesses? So okay, let me start. I do a sum over all outcomes. Yeah?
It would be, well, it would be the sum of, it's the sum of the product of the product of the probability of that outcome.
Yes.
And you'd also need to assign like a value to the outcome itself.
Which is exactly what the random variable does. The random variable, by definition, is sort of saying it maps outcomes to some number,
Okay.
right?
So the product of the probability of the outcome and the random variable.
And the random variable at that outcome, which is now not a random variable, it's fixed at that outcome, right? So formally, it's the probability of that outcome times the random variable at that outcome. And I could also use these braces here. It's all the same. But usually with expectation, at least in most of the books in theoretical computer science will use square braces. But it's the probability of the outcome times whatever value there is at that outcome, right? This is average. Does this make sense? How many of you have taken a statistics course? Most of you have. Okay, so this isn't news then. Probably it's just written in a different way. Maybe in a statistics course you'll see an integral here. And you see an integral because this isn't discrete. But it's all the same, yeah?
When I took it, this was described as the expected value of,
Yes, this is the expectation or the expected value. Yes, they're both the same thing. Expectation, expected value, average value is probably not used as often, although it means the same thing. This is probably used maybe in more non-mathematical language. But it means the same thing. When they say average value, they probably mean the expectation or the expected value. And this is the expected value of this random variable. So now with all these definitions in place, we can actually start talking about randomized quicksort. Because we can say for any input, what is the expected running time? Right? It doesn't help us analyze it, but at least now we know how to write down what we want. Questions? Okay, let me continue. So, I'm going to remove. Have you heard of linearity of expectation? No. Okay. No, yeah. So, sometimes if you have two random variables x1 and x2, you can ask, what is the expectation of the sum? What is the expectation of the sum of random variables? And there's a statement called linearity of expectation, which basically says that the expectation of the sum is the sum of expectations. And we can prove it right now. It's not particularly hard. So let's say you have a sum of k random variables. So sum commutes with the expectation. This is called linearity of expectation. It just says that if you take the expectation of the sum of random variables, you get the sum of the expectation. It's the same thing. Let's go ahead and prove this. Unfortunately, it's a very innocuous looking statement. But if you think about it, what it allows you to do is to say, you're trying to understand what's happening at the sum, but it's enough to just understand each one of them individually and just sum up the results. And we'll actually see why this is a powerful statement. So I'm going to get rid of this. So let's actually prove linearity of expectation, we'll just prove this case here. We'll just prove the one with two of them, and then you can use induction to get there. So the proof is, I mean, it's actually not even much to say. It's simply just write everything down. So what is this? Well, this is the sum over all outcomes of the probability of the outcome times the value of this random variable at that outcome. Right? So what is the value of this random variable? Well, it's just x1 omega plus x2 omega, right? I mean, this is just some random variable, this is another random variable, given a particular outcome, this gives you some value, this gives you some value, and then, you know, sort of you do the obvious now, you basically break up the summation, the probability this times that, plus probability summing over all omega, probability omega, x2 omega. Does that make sense? So what's really important here is you don't need to assume that they're independent. The product of expectations, if you want to break it up, then you need to assume they're independent. But this doesn't assume any independence. It assumes nothing, because it doesn't need to. You just have to break up the sum, you break it up this way, and what is this thing here? What is that thing? That's the expectation of x1, and that's the expectation of x2. Right? So you see, right? So you get the expectation of x1 plus the expectation of x2. Sorry, the proof goes that way. Right? So you start from here and you go there. It's not like you start from there and then you go there. So this is equal to this is equal to this is equal to this is equal to that. And that completes our proof. And if you have more of them, then you do induction. That's usually what happens when you have more stuff. You prove it for two and then you just do induction. So you can use induction to basically prove it in general. But this is what's happening, and it's not particularly mysterious at this point. Right? Okay. There was actually, okay, so now that we have linearity of expectation, there's one more thing that I need to say. And after that we will be all set to go. There's a special kind of random variable called an indicator random variable. So given event E, the indicator random variable, let me call it x, basically, remember, x is a function, right? So x of some event is 1 if omega is in the event and 0 otherwise. So it simply indicates whether your specific outcome is in the event. Does that make sense? So now let's see how well you understand this. What is the expectation of this? What is the expected value of this random variable? You should be writing, not staring at me. Like, write out what the formula is, and you might see it. Like, write out the expectation as the sum over all outcomes, right? Of the probability of the outcome times the value. And then you'll kind of see what this is. Yeah, any guesses? Someone other hand. Yeah?
Is it the probability of T?
It's just the probability of the event. Right? Because if you write this out as the sum over all outcomes of essentially whenever omega is not in the event, this just disappears, it's 0. So you're only left with omega in the event of the probability, I'm sorry, this should be omega of this, which is exactly the probability of the event. Right? This is the probability of the event. So the indicator simply says, does the event happen or not? So this is a 0, 1 random variable. It's a bit. But the expected value of this bit, the expectation of the bit, is the probability. These are also referred to as Bernoulli's, as Bernoulli random variables. But we don't need to get more into the behavior of Bernoulli's. But this is actually very, very useful in the analysis of randomized algorithms, is to try to write things in terms of indicators. Right? And so going back to our picture over here, if this was your set of outcomes, this is the event, then the expected random variable, the x is basically 1 here and 0 everywhere else, and the expected value of x is just what is in here. Sometimes, yeah, let's ignore other notation for this, but this is the indicator. It's also, I'll tell you. Sometimes they also use this notation, a bold 1 with the event. This is the indicator random variable. Statistics texts will often use that sort of notation. Okay. Questions? Okay, now let's come back to Quicksort. Now we've learned all of the stuff. We've digested everything. We know what it means. Let's do Quicksort. So let's come back to randomized Quicksort. So, we agreed, what is the space of outcomes? It's all the pivot choices. Right? For any fixed pivot choice, you have a running time. So the running time is a random variable over the outcome space of pivots. Now I'm going to write the running time of Quicksort in terms of indicator random variables, and then basically apply expectation, linearity of expectation. So let me keep this over here. Let's get. So just for convenience, let me look at the random variable that is the number of comparisons made on a, okay, so fix an input. Fix input to randomized Quicksort. So let's start with that. So we fix some input. Now let's look at the random variable, that's the number of comparisons made. Right? Let's just ignore data moves because it'll be the same thing. Okay? So how many comparisons does randomized Quicksort make? So recall, at every stage, if you choose a pivot, if this is the pivot, everything is compared with the pivot, but that's it. And then it's done in the recursive calls. Right? So anytime there is a comparison, one of them is the pivot. Does this make sense? And this is really important, right? Anytime there's a comparison, one of those things being compared is a pivot for that recursive call. Okay. So how am I going to write this? So this is the input A. Let me say S is just the sorted ordering of A. It'll be convenient for me to talk about things in terms of S instead of A. And given any I and J, I just want to, okay, so no, let me, this, the number of comparisons I'm going to write as the sum over I less than j, right? This is whatever, 0 to n minus 1 of xij, where xij is the indicator for Si, I'm going to write this as a subscript, okay? Si compared with Sj. So all I'm saying is, okay, I want to understand how many comparisons there are, and I'm just going to ask for every pair ij, not with respect to the input, but with respect to the sorted order. It's all the same. For every pair of elements, is it compared or not? Right? This is an indicator. And when I say ij, I mean whether si is compared to sj, not whether ai is compared to aj, but it's all the same. The sum is the same, right? It doesn't matter whether I'm summing here or here, but it's going to make life easier for me in the proof. But I'm just going to write my total number of comparisons as this sum. And it's a sum of indicator random variables, right? So this is going to be 1 if it was actually compared and 0 otherwise. So clearly the number of comparisons is this, right? So far nothing fancy has happened, but the next step is going to be fancy. Is this clear? Okay. So now you watch the magic. Like now this is where like rabbits start popping out of hats. So you say, okay, what is the expected number of comparisons? Right? Because this is really what you cared about. You say, okay, I'm just going to say that's the expectation of the summation of I less than j of x ij, right? But I can use linearity of expectation now. And I get the sum over I less than j of the expectation of xij. This is remarkable because if you really think about it, these random variables are all dependent. Like, depending on what the first pivot was, the second pivot would be different, and they all interact with each other in some complicated way, which is what makes it really hard to analyze randomized quicksort. But when I use linearity of expectation, I only have to worry about whether a specific I and j are compared. Right? And this, by the property, is simply the probability that Si and Sj are compared. So this is really remarkable because instead of trying to understand how randomized quicksort works as a whole, all I have to sort of figure out is for any I and j, what is the probability that they are compared, regardless of what happens to everything else. And I just sum up those probabilities. And this is even though these are all dependent. This is linearity of expectation, and this is simply the fact that it's an indicator random variable. Right? So this is linearity of expectation, and this is because this is an indicator. Right? This is an indicator random variable, so the expected value is just the probability. Yeah.
So just to clarify, this trick wouldn't work if it was like a weighted probability for each pivot. Correct?
Even if it was weighted, I mean, if you can express something as a sum of random, like the average value of the sum is the sum of the average. This sort of always works. The trick is to be able to write whatever you care about as a sum of simple things, and then we still haven't figured out how to do this. Because this also isn't obvious, like it's not obvious what this is going to be. But what this allows you to do is instead of trying to worry about the whole, you get to worry about a specific part. Which is just, I have two elements, are they going to be compared or not? And then you can kind of sort of just add those values up and get the average. Right? So if you actually look at randomized quicksort from afar, it looks like this is a mess. Because the choice of the first pivot affects the sizes of the next, which is going to affect the choice of the next pivot, and the pivots all sort of depend on each other. Whereas here it says that if you can just figure out for any I and j, what is the probability that Si and Sj are compared? If you can figure out some formula for this probability, then you just sum that formula up, and that gives you the expected number of comparisons, which basically bounds the running time of Quicksort. Okay, so it's sort of remarkable, even though you just use linear. I mean, you use a simple formula, but it's very clever. Like, I mean, I think this is not the original analysis. This is like Karp's analysis. Is very clever. Okay, but I have to tell you how you get this. Okay, so now, by now we've used linearity of expectation. I can get rid of this now. So this goes. So in the interest of sort of showing you the main idea, I might not write out the next thing completely formally, but hopefully it should give you enough of an idea. So I'm just going to look at A and S. And so you have Si and Sj. And you want, what is the probability that these are going to be compared in some like recursive call, right? Not just in the top recursive call. Okay? So in the very, okay, so let's sort of make a few observations here. So there are really, I'll say there are 4 choices. Well, okay, we can even look at this and say there are 5 choices of the pivot. This is the sorted order, right? The pivot, remember, the pivot is chosen randomly from A, which is the same as randomly from S. So the pivot is either here, 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 or here. Right? What happens if the pivot is here? What happens to I and j? Does this make sense? So let's say you pick the pivot, and it happens to be here. So you pick the pivot, it happens to be here. What is it going to do? It's going to move everything less than the pivot to one side and everything greater than the pivot to the other, right? So what happens to Si and Sj, yeah?
Si and Sj will fall on the right side.
They'll fall on the right side, but they'll be together. And then there's some recursive call that's going to handle what's happening there. What happens if it falls there? Yeah? They both go to the left, and then recursion, we don't know what happens. What happens if the pivot fell in here? They split, which means they'll never be compared, because they go into separate calls. You're trying to understand what is the probability that Si and Sj are compared, right? So if the pivot was chosen in the middle, they'll never be compared. You want to actually make this probability as small as possible, because that's how you'll get this thing to be small, the number of comparisons. So if the pivot was chosen in the middle, they'll never be compared. If the pivot is chosen to be either I or Sj, then they will be compared, obviously. So let's just write out these outcomes, okay? So case 1, and there are really 3 cases, is pivot is Sk, where k is less than I or k is greater than j. Then both I and j end up in same column, right? But it's a little more than just I and j. All of this ends up in the same column, right? Because the pivot is chosen here or here, all of that just moves to the left or to the right. Both I and j end up in the same call. I'll say all SL, where L lies between I and j, end up in the same call. Right? Case 2, pivot is Sk, where k is between I and j. Then Si, Sj never compared. right? Regardless of what happens in the rest, right? Because they went to separate recursive calls. And let me go here. So by now, hopefully you remember this, because if you don't, then at this point, you have no idea what's going on anyway. Right? So I can remove this. And case 3 is that Si or Sj is the pivot, which means Si, Sj are compared. So in this case they're compared, in this case they're not compared, and in this case it basically is decided in a recursive call. But intuitively at some point, one of these is going to happen, right? Eventually, one of these is going to happen. Does that make sense? So consider the first pivot chosen in SL, where L goes from I to J. So at some point, one of these is going to be chosen as a pivot. Like the first pivot. Which were case 2 or case 3. So if case 2 happens, they will not be compared, and if case 3 happens, they will be compared. So now, what is the probability of case 3? Assuming that the pivot is chosen amongst this. Remember, all of these are sitting together in some recursive call, right? And I'm telling you one of these is chosen as the pivot. What is the probability that the first pivot chosen amongst these is either Si or Sj? Yeah?
Would it be 1 over I minus j or j minus I?
Good. It's 1 over, or 2 over j minus I, because like I would be Si or Sj.
Oh, okay. Yeah.
But exactly, right? And it's j minus I plus 1. But yeah, you got the idea. The pivot is chosen randomly. It doesn't prefer any one element over the other. So the probability that either Si or Sj is chosen as the first pivot is the two choices divided by the total number of choices, which is j minus I plus 1. So the probability that Si or Sj is the first pivot in in this range is actually equal to 2 divided by j minus I plus 1, because that's how many numbers there are. It's like j minus I plus 1, right? So we've actually nailed down what the probability that Si and Sj are compared is. Which means we can plug this formula into there, write out the sum, and then we end up analyzing quicksort. Well, how long do I have? 5 minutes?
10 minutes.
10 minutes, okay, 10 minutes should be enough, yeah. So I don't want to actually remove any of this, right? I want to write so that we keep all of this so that I can walk back through it. Does this make sense? This is remarkable. So basically it's like, you sort of carefully piece these things together and then the analysis becomes fairly short. What we say is, to understand whether Si is compared to Sj, let's just look at the pivot choices. If the pivot happens to be either here or here, well then both I and j move together, or actually that entire block moves together. If the pivot is chosen in the middle, they will not be compared. If the pivot is chosen to be one of those, then it will be compared. And you know that at some point, something in here has to be chosen as the pivot, as the recursive calls keep moving. So the question is, what is the first pivot that is chosen within this range? And the probability that Si or Sj is the first pivot is the two choices, which are I and j, divided by j minus I plus 1. Right? And so we just need to we'll plug this into that formula, and then I'll work that out. But does this make sense? So this, again, is sort of the remarkable use of linearity of expectation, is that once I get this formula, because I only need to worry about what happens with I and j, I can I can basically analyze this more complicated process. Okay? Now it's not gentle anymore, so I removed it. Now things are getting more complicated now. Okay, so we said the expected number of comparisons, and in this case it's an equality, so as we said, it's the sum over, so I'm going to write this out as 0, so I going from 0 to n minus 1, j going from I plus 1 to n minus 1 of 2 divided by j minus I plus 1. Right, that's the sum. Okay? So I'm actually just even going to, so the factor, the 2 can come out over here. And I say j going from I plus 1 to n minus 1, it turns out that I'm actually just even going to ignore the minus I. Well, no, I can't do that. Right? This is going in the wrong direction. So, let me write this in the following way. What do I have in mind? So what is the simplest thing that I have written down? Okay, my notes are incorrect. Doesn't matter. So, just think about like what this is going to be for any choice of I. It's going to first be, let's just look at this thing, right? It's going to be 1, 2, 3, 4, so on and so forth. Going all the way, at most, up to n minus 1. Right? So I'm just saying that if you fix I, then what this thing is going to be is it's going to start by going 1 divided by 2, 1 divided by 3, 1 divided by 4, all the way up to 1 divided by n minus 1 plus I minus 1 plus 1, sorry, which is basically you get 1 divided by n minus I. Right? Another way of thinking of this sum over here, ignoring the 2, ignore the 2. It basically goes from 1 over 2, 1 over 3, 1 over 4, up to 1 over n minus I. So I'm going to be really loose over here and just say, well, I'm just going to assume it goes all the way up to n. It's an upper bound. So I'm just going to take j going from 1 to n and just write 1 divided by j. Okay? I'm just going to say this thing, it only goes up to n minus I, but I'm just going to upper bound it by going all the way up to n.
Sorry, 1 over n?
Sorry? To 1 over n.
Oh, yeah.
To 1 over n. Right? I'm just saying, you put in more terms because I'm giving an upper bound. So this thing doesn't even depend on what I is. Right? It's just n times this. Right? So this is 2n, I'll write it here so that you can see over there. It's 2n summation j going from 1 to n of 1 divided by j. This thing has a name. It's the sum of first reciprocals, right? Has a name. It's some other, yeah?
Harmonic series.
It's the harmonic sum. The thing is the harmonic series, and this is the harmonic sum. How much is this thing? Well, you can say it's the nth harmonic number, but what is the nth harmonic number? You guys know what this thing roughly is? Yeah?
Is it E? No. I was thinking the wrong thing.
No, you're sort of, some portion of your calculus brain is fired, and the first thing that fired said E. It's like, okay, E must be the answer, yeah?
Aspirant 6.
Sorry?
Aspirant 6. No.
Pi squared on 6 is when you put j squared and you let that go to infinity. Yeah?
Is it infinity? Or no?
It's n, right? It's a function of n. It's a function of n. You know how I keep cribbing about your calculus education? Watch. I'm going to write this calculus expression. You know immediately what the answer is. What is that? Natural log of n, right? That's what it is, right? Because this, it's the same thing, really. A summation is an integration. This is the natural log. Up to a con. You were going to say something else? Or?
Nothing's enough.
Okay, all right. It's this thing, the nth harmonic number, is technically log n plus theta of 1. I mean, it's log n plus something. The point is, this thing is at most like 2 log n, whatever. So this is O of n log n, right there. Because this is the harmonic number, and we're done. So that actually completes the analysis of randomized quicksort. It's the other way, the other way of analyzing a randomized quicksort is to write out the recurrence and like average over all the recurrences, and it's this big mess, and then you apply induction on top of it, which I had done once in 101 and realized was a bad idea. But the point is, this is a very slick way to analyze randomized quicksort. So let me just sort of, okay, so any questions? I'll walk back through the whole thing. Right, so let's go back to sort of the beginning, because I think the proof goes from right to left. Right? So we said, we want to know what the expected number of comparisons is. So we can write that by saying, well, it's basically, let's sum over all pairs and check if each pair is compared. And we'll do compares, all pairs in the sorted order, but that doesn't affect the total number. So we'll write this as the summation of I less than j of xij, where xij is the indicator for I being compared with j, si being compared with sj. Right? That's actually written here. Right? So the number of comparisons I'm going to write in this way. Summation of xij, where xij is the indicator for si being compared with sj. Okay? So now that I write that, I take the expectation of that. That's the expectation of this sum. Now I do this magic step. I say, let me do linearity of expectation. So I switch the sum and the expectation. So I have the sum over I less than j of the expectation of xij. This is an indicator random variable, so it's simply, this is the probability of the event being indicated. So this is the sum over I less than j of the probability that si and sj are compared. So now I can try to get some formula for this, plug it back in, and I get a sum. And I get, I get whatever, my bound for the expected number of comparisons. So now let's try to understand when si is compared with sj. So when you think of the sorted order, and the pivot is chosen at random, just at the top level call, there are 3 cases. The pivot either lies here or here, right? The pivot is sk, where k is less than I or k is greater than j, in the very first call. Which means in this case, all of this range is just going to end up in the same recursive call. In which technically, if you wanted to then prove it, you'd say you have to do some kind of induction on what's left. But everything in here lies in the same recursive call. Case 2 is the pivot lies in the middle. And if it lies in the middle, then si and sj go to separate calls, will never be compared to each other. And so really what we're trying to understand is the probability of the third case, which is si or sj is chosen as the pivot, in which case they're compared, or technically we have to understand when si or sj are chosen as the pivot before something in the middle is chosen as the pivot. And so let's consider the probability of the first pivot being chosen, consider the first pivot chosen in SL, where L goes from I to j, and we want that to be si or sj. That's when they'll be compared. And this probability is exactly 2 divided by j minus I plus 1, because there are 2 choices, I and j. And the total number of choices is the total number of choices for L, which is j minus I plus 1. Right? And so we take this and we plug it back into that formula. And so we get this double summation. Summation over I and j of 2 divided by j minus I plus 1. Now, to understand this, remember that you are summing over a fixed I, and you're looking at j plus I, and so it's, if you look at basically ignoring the 2 factor on top, it goes 1 over 2, 1 over 3, 1 over 4, up to 1 over n minus I. And I'm just going to give an upper bound. I'm going to say, well, I'm just going to assume it goes all the way up to n. So I get the sum of I going from 0 to n minus 1, that stays. This is just the sum of j going from 1 to n of 1 over j. And this is the nth harmonic number. And so it's just 2n times the nth harmonic number, which is O of n log n. And so that completes the proof of the expected number of comparisons that randomized quicksort makes. For a high probability statement, then you need more work. But okay, so let's end there.
Nice.
So,